Hello. My apologies. I didn't send this earlier. It's so hard to get a good teacher anymore. However, if you knew how many live streams I was doing each day, you'd understand how I'd get screwed up. Good gosh almighty. Anyway, thank you for being here. So I got Alex, Louisa, Ellie, and Oscar. And Alicia. Good. We're a third of the way there. Yeah, so tomorrow I have an ED meeting, so we can only meet from 12:20 to till 1 o'clock, and then I have my meeting. So we have to make it short tomorrow. So it's good that you can meet today. Hope others can make it. Sorry it was last minute, not my usual way of doing things, but alas, I screwed up today. Okay, we'll begin with some questions from you. So while others are arriving, we can go ahead and start. And let's see what questions you have on chapter 1. So let me know what's on your mind, and we can maybe work on some stuff together. Good. Who else is here? Errol is here. Super. I'll put that aside. And I did send to you, I hope, chapter 2, so everyone should have that, including Oscar. So you can work on that whenever you get that far. I put what I think is a reasonable due date on it in Google Classroom. So hope that works for you. We don't have class next Monday, I believe, because it's either President's Day or Martin Luther King Day, one or the other. So our next class will be a week from today after a short class tomorrow. And Chelsea's here. Good. Almost half of you. We'll see some others show up. Okay, any questions on chapter 1? Anything bugging you so far that we can look at together? We are almost done, by the way, with chapter 1 ideas, which is sort of good to know. And I think we had catalyst all done. Yeah, we had that. Okay, good morning. Okay, anybody else? I got 10 of you, so I should have 1 or 2 more. Say hello if you haven't said hello yet. Right, that's where we ended off. If not, I got plenty to talk about, so don't worry about that. Okay, so I'll set that aside for now. Yeah, we're actually about done. Okay, so Antonine, good morning. Now we are over halfway there. Hope the others can join us, but if not, I'll send them the video. Okay, so let's get this so you can see the whiteboard a little bit better. And if there aren't questions on chapter 1, let's finish the sucker up. So we talked yesterday about catalyst, okay? The only last thing we need to know about catalyst, which will make total sense to you, is let's draw a little PE diagram. And you know that's stages of the reaction, so I'll go like this. And we learned yesterday that a catalyst looks like that. So a catalyst lowers the energy. So what does the catalyst lower? The energy. Somebody type in an answer. Thank you, Chelsea, Alicia, and others. Okay, great. So just a note here so you can think about this, okay? Note, a catalyst lowers the activation energy, so EA is the shorthand for that, by the same amount whether you go in the forward direction or reverse direction. Reverse direction. Here's what I mean about that, okay? So if I add the catalyst, it saves us this much energy. But it saves that amount of energy whether I'm going this way or whether I'm going this way, backwards or forwards, okay? That's all that they're trying to say about. Good, I got a couple others that joined me. Thanks for saying hello. So I got Penelope now. Sorry this was so last minute, everybody. I've got Amina as well. Super. Okay. Good. Thank you for joining us, Amina. Again, not my usual way of doing things. Sorry about that. I thought I'd send it out 2 days ago. Okay, I believe that takes care of. No, I'll take it back. Okay. Yesterday, I think just as we finished up, we talked a bit about oranges. Who was the person I picked on this year? Who liked the oranges? Who was my orange eater this year? I picked a person random, and now I've done this so many years I can't remember who it was. Who was my orange eater? Chelsea, it was you. Okay, all right. So what was the point of that whole thing? Okay, the point of that whole thing was essentially about, we got actually more to do. I know what I forgot to do. Yeah, we still got some more to do, but it's okay. The point of the whole thing, point of the oranges example was this: to speed up the overall rate of a reaction, you have to speed up the slowest step. Which only makes sense. So it doesn't matter how fast Chelsea ate those oranges. It only matters how quickly we could get the oranges somehow to her. Okay? So we got to speed up the slowest step. What's that slowest step called? Did I give you that name? It's called the step. Just checking to see if we have that in our notes. That slowest step is the step. If we don't have it, we're going to have it soon. Oh, we do have it. Thank you, Chelsea. And Bella is here. Okay, good. So rate determining step. Good. If I can speed that up, I can speed up the overall reaction rate. Dynamite. Okay, I want to look at a couple reaction mechanisms with you now. And I got an overhead, which I know is sort of stupid, but let's see if I can hold it up, if I can put my hands on it. Hold on. There it is. Okay, so you might even be able to see this, but you get the idea. Okay, so voila. Boop. Way too far away. Okay, so let's bring you closer. You ready? You gonna stay there for me? Yeah, with a little lickum it does. Okay, so here we go. You ready? We're going on a journey. Don't get sick, anybody. Okay, here's the reaction at the top. You there? Yeah. Look at this reaction at the top. 5, hell, let's just write this bigger. I'm not going to write all this, but I'm going to write the reaction. So I got 5 Fe, 2 pluses, plus an MnO4 minus per manganate ion, right? MnO4 minus, plus 8H pluses, forms blah, 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 blah. Okay. How many particles would have to hit here? How many particles would have to collide all at once to make that happen? Count them up. How many particles would have to collide to make this happen? Anybody out there? Count them up. 5, 1, 8. How many particles would have to collide? Ah, there you go. Okay, so, right? You guys need a little help on your counting skills. 5 plus 8 is 13. Plus 1, right? 14. Yeah, that sounds better, right? So 14 particles colliding. And the answer is no freaking way. Excuse my French. So that reaction, and maybe I'll draw the rest of it now. So it makes 5 Fe3 plus Fe3 plus 4 waters plus an Mn2 plus. That reaction, folks, is only the net reaction. Or you could say it's the overall. That's the better word. This is the overall reaction. The steps to get that reaction are in the reaction mechanism. So a new word there, or new phrase. So that's the overall reaction. Okay, fine. But that's not the steps. The steps are in the reaction mechanism. And that's what I'm going to show you as soon as I give you a chance to write that down. Okay? Okie dokie. I need some whiteboard. So I'm going to lick this thing and put it back up here. Stay up there, would you? Hey, that works pretty good. Okay, now I'm going to bring you in closer, all right? Don't get seasick. I want you to look at some of the separate steps that are in this mechanism. So, check this out. I've got the first step, Fe plus 2 plus MnO4. That's got how many particles hitting? 2, right? Look at the next step, MnO4 2 minus plus 2 H pluses, 3 particles hitting. Look at the next one, MnO3 plus Fe plus 2, 2 particles hitting. Here I got 3 particles, 2, 2, 2, 2. Do you see how that's more likely? Just 2 or 3 particles hitting? Really, other than about 4 particles hitting, you just don't get any more in a step, in a reaction. It's too many. Now, think about the problem back here. Look at it, 14 particles, here they come. They don't even fit at one spot. So there's no way I can have 14 particles all colliding at one particular spot. The most I can have in any step is 2, 3, 4 particles colliding, okay? That is it. There's just not enough room for this to physically happen. So what I want you to get out of that is just exactly that idea. Most steps have only 2 or 3 particles in the collision. Most steps in a reaction mechanism have only 2 to 3 particles colliding. The odds, the probability is much higher that that's going to happen than a lot of nonsense of 14 things joining at one spot. Okay, good. All right. And I see Lola's there too. Thank you. Just write that down. So I got most of you. Good. Two, three. So I just missing 3 of you. Missing Anne-Sophie, missing Aiden, missing Feeny. So Anne-Sophie, Aiden, or Feeny, any of you there? Okay. Let's go on. Here's some advice. If I got a big, long set of steps like this, steps in the reaction, it's often the first one that's the slowest step. Not always, but I'll just say often the first step is the rate determining step. Determining step. Not always, but often, okay? Ute. Let's take my funny sheet down. And while you catch up, let's find what I wanted to talk to you about. Everything's so crammed in my little office here. Yeah, that's what I want. Okay, so here we go. Let's do a couple reactions, okay? Now, the one I showed you had a really big mechanism, didn't it? So it had a whole lot of steps. They don't all have that many steps. Let's do one. Good gosh, I can't do anything today. Here we go. Let's do one that has 2 steps. Okay, so example. Here's a reaction mechanism. So we got NO2 These are all gases, so I'm going to leave out the phases, plus another NO2 forms NO3 without a charge, plus NO. Okay, and that is a slow step. And then I got CO plus NO3 forms CO2 plus NO2. Is that right? That does not look right to me. I think it's NO again. Let's see if that balances. 4, that's got to be NO2. It doesn't really matter. That's a fast step. Okay. So what we've got are 2 steps in our mechanism. Okay. Obviously, 2 steps. And lo and behold, the first one is the slowest one. So that's going to help me figure out the rate. Now, let's combine this with something else we already learned, a rate law. You can pretty well guess a rate law based on the slowest rate determining step. Okay, so base your rate law on the rate determining step. And we only need the reactants, right? Where did the C come from? Let's just say it's another chemical that's out there. So it's in my bag of chemicals, Amina. Yeah, it doesn't have to be here in this step. It's in the bag of chemicals I've got. It doesn't need to be in the slow step, no. Okay, so base your rate law. So here we go. So my rate for this is going to be based on these reactants, NO2. Well, first there's a little K, right? The rate constant times NO2, concentration of that. But to what power? To what power? Well, check this out. There's 2 of them. So guess what? You guessed it. It's to the second power. Ta-da. Good. Let's do another one. Yeah, I see that. But you know what? The deal is, Lola, that is a faster step. So it's not really going to determine the rate. It's going to be too fast. That will be like Chelsea eating the oranges really fast. It doesn't matter. It's part of the reaction, but it's not determining the rate of the whole thing. Okay? Only the slow step is really determining the rate. Let's do another one. Let's do another one with gases. NO plus Cl2 forms NOCl2. And that's going to be fast. And this time the slow is the second one. So I got NOCl2 plus NO forms 2 NOCl. And that's slow. And let's do the overall. So I'm going to add this together. and say this is the overall reaction. Okay? But, before we have the overall reaction, is there anything that kind of cancels out here if we're going to add these steps up? Like that big one I showed you, I had to add up like 10 steps. Here, when I add the steps up, what's going to drop out? See if somebody can follow. I'm going to add these two together and get one reaction, but something's going to drop out. Thank you, Oscar and Amina and Alicia. You're right. This is the same on the product and the reactant side of two different steps, so it crosses out. I'll tell you what it's called in a second. Let's write what's left. So what we got is, oh, look at this. I got two no's. I got a no-no. So I got 2NO plus Cl2 forms 2NOCl. Ta-da! Okay, now, this thing that canceled out is called an intermediate. Yeah, Penelope had that too, as did Lola. Good. So, an intermediate is a chemical species, as they call it. So a species, like an exotic bird, but not so exotic, a species produced in one step and consumed in a later step. Now, it's not that they're that interesting, but here's something you got to know about intermediates. Ready? Here's our German. Achtung! No intermediates can be in your rate law. And this will be a multiple choice question every year on the AP test. No intermediates allowed in a rate law. So that's going to change how we do things. All right, I got to race a little bit. So as soon as you're done writing, I'm going to race here. I wish I could see you writing. I'll send you the video later anyway, if we don't get cut off, and I hope we don't. We're doing okay time-wise. Okay, so I need to erase all this down here. So intermediate, a species produced in one step and consumed in a later step, and no intermediates allowed in a rate law. Okay, bye-bye. So now let's work on the rate law as if this was a multiple choice question. Let's do it in red for grins. So the rate, well, we're going to take the slowest step, aren't we? Because that'll be the rate determining step. Rate's going to be K times, look at what's there, NOCl2. Yes, I know. Times NO. My dad used to say that gas a lot to me. Okay, so that's my first guess, but this is not allowed. So we do something clever, okay? If it's not allowed, it's okay. You're going to substitute something in for that intermediate. Look where it comes from, NOCl2. Ah, it came from the NO plus the Cl2. So substitute from a previous step. And that, my friends, is not very hard to do. So that's my clever suggestion for you. Times it by CO2. Yeah, exactly. So here's what we're going to do. So kind of get rid of that sucker. And instead, we're going to rewrite it. All right, so the rate is equal to K times, okay, where did that come from? NO but check this out. I got NO and NO. So actually, I got one of the slow step and one that it came from previously. So it's NO now to the second power, right? That one and the one I substituted in there times the concentration, I think Amina said it, of CO2. And that, my friends, is your rate law now without an intermediate in there. See how slick we did that? So substitute in from a previous step to get rid of your intermediates, okay? So intermediate, not allowed. Intermediates, not allowed. Yeah? So we can get rate laws like this either, to wrap things up, either from a reaction mechanism or from data, the way you did it previously, where you had different rates and different concentration changes, and then could get the rate law with that. All right, got it? So don't let that all be a weird. So rate laws from one, reaction mechanisms, or data. And now you've done it, there goes my notes. Now you've done it both ways, haven't you? We did this one with our data that we've got, our reactions, our rate determining step, and so on. But you've done it from data quite a bit already. Okay. How do we get the second power? Good question, Oscar. Let's look back. Okay, the rate determining step, the slow one, was this, and it had an NO in it. And then I got to substitute for the NOCl2, I got to substitute these things. So it's sort of like this, Oscar. I got to take this down and shove it in here. So I got an NO plus a Cl2 plus another NO. So that makes no. I got two no's here once I push this down. And so it's no to the power squared. Hope that helps. Yeah, and Amina said the same thing. Thank you, Amina. Good. Dynamite. I should have looked. She answered already for me. Okay, let's see if we got another one that's kind of cool. I'm going to have you guys try one. Ready? So here we go. Your turn. So find the rate law if you get these. Here's your three steps. 2NO, our special gas today, goes back and forth, but it forms N2O2, and that's fast. Second step, N2O2 plus H2 forms water. Plus N2O. And that sucker is slow. And finally, we got N2O plus H2 forms N2 plus water. That sucker is fast. Not flast. Fast. Okay, so your turn. What's the rate law? So write it down. My hint is cancel out your intermediates and then figure out how to get the rate law based on what we said last time, okay? So I'll give you a couple minutes to do that. Let me read it again in case my writing's blurry. 2NO forms N2O2. N2O2 plus H2 forms H2O plus N2O. N2O plus H2 forms N2 plus H2O. Fast, slow, fast. All right, so try and write her down. And if you can't find brackets, just use parentheses or something, okay? And try and type in the chat tool your guess. I'll give you a couple minutes to make your good guess. And Alex has a guess, and I'm going to let a couple others come in if you're still typing. In fact, while you're typing, I'm going to cross out a couple things. All right, all right, all right, all right. If you think about it. Good, I got a couple other one into the bracket. Shell? I don't quite understand your comment, Bill. Okay, so good. I got several here. Exactly. You bring the coefficient not into the bracket though. Okay, so here we go. Yeah, that one stays in there. Okay, so we got K times. Good. So the ones I've seen so far, Amina, Bella, Lola, Alicia, have taken the slow step, and certainly it's going to have H2 in there. But that sucker's coming from NO, and there's two of them. So nicely, all of my guesses so far have NO2 squared. And do I care which one is first or second? I don't. I don't care because it's all multiplication, right? Doesn't matter from math class. But you got to have the H2 in there because that's in this slow step also, okay? Good. What if this question also asked you for the intermediates? What are the intermediates? So what if they ask you for the intermediates? What are they in this reaction mechanism? Type them in real quick. Peachy. Swelleroonie. Thank you. Good. Let's see if a couple more come in. Oh, they are. Ooh, they're flying in now. It's Antonine and Bella and others. Good. So there are two of them this time. There's the N2O2. that we used to substitute our two NOs for. And there's this other one I crossed out. N2O is also an intermediate. It's formed in one step, used in a step right after that. Lovely. Good. Chapter 1, finito. Finito. Let me look, but I think that's it. We've done everything and more that we should. Did I already give you that one? Yes, I did. So we can't do that again. Do I have another one for grins? Probably not. Probably not. Okay, so be it. That's all right. Yeah, it's okay. It's all right. Everything's good. Everything's good. Let's take a quick look at. Actually, let's keep this for a second. Let's take a quick look at the book. But I believe chapter 1 is done. Yeah. Beautiful. Look at all that. We've covered a lot. And that's a juicy chapter, chapter 1. Okay, chapter 2 is also juicy. And chapter 2 is about equilibrium, which is kind of fun philosophically, too. Okay, so chapter 2. Equilibrium. You can think of a little Buddhist chant. Okay. Why am I doing that? Because we're going to put our hands out in a second. You'll see why. Okay. Okay, let's take a let's take an idea here. Let's say we got reactants and over here products. You and I are going to start using double arrows. Here's what I mean about that. We're going to say, well, you know what? The reactants can become the products, or the reaction can go backwards. The products can become the reactants. So it can go both ways. All right, equilibrium is when the forward and reverse rates are equal. How can this be? Because I have different things that could be happening in the beaker. I could have something forming and then also something breaking up on the other side, okay? Why? Because I got a beaker with lots and lots of molecules. Some of them may be forming and others may be pulling apart, okay? So I can have both things happening in my beaker. I got a lot of molecules in there to play with. You know you got equilibrium. EQ for short. You know you're at equilibrium if there's no change in So what do you suppose will stop changing if I'm at equilibrium? There's more than one answer. See if you can give me something that will stop changing once I hit equilibrium. It doesn't mean the molecules have stopped, by the way. They're still going back and forth, okay? So what's something that will stop changing at equilibrium? Once I hit equilibrium, what will stop changing? Concentration. Thank you, Lola. Sometimes we can see that by the color. So I'll put in parentheses color. Some ions have a color, and I know a lot of them don't, but sometimes color. Good. Anything else? Temperature, Oscar. Righto. So if the temperature stops changing, stops going up or down, you're at equilibrium. Volume, not necessarily, Anthony. Depends on the reaction. Actually, I take it back. Volume, yes, Anthony, but it affects something else if there's gases. So what else would not change, Anthony, if the volume is the same with gases? Hint, Pivnerd. If the volume's the same, what else would be the same if we're talking about gases? Exactly, Anthony, the pressure. So if all those are now constant, they're not changing anymore, congratulations, you're at equilibrium. So what does that mean? What does that mean? I need something. Usually I can do this with a piece of chalk, but I don't have that. So we're going to play a game here. Okay, who haven't I picked on in a while? How about Alex? I haven't picked on Alex for a while. So Alex, you get some candy. How lucky are you? Too bad you can't eat it because you're not here. But what you're going to do is I'm going to give you 5, and I'm going to keep in my hand 4. Okay, so this is going to be like our reaction, everybody. You ready? Yeah, it's a closed system. Thank you, Mina. So is my candy. I got 9 pieces of candy. Okay, it smells kind of good too. I got to eat some lunch. Okay, so what's going to happen is I'm going to make a reaction, and the reaction is I'm going to send over a piece of candy to Alex, and he's going to send one back to me at the same time. And I'm going to do that again. I'm going to send one over, and he's going to send one back at the same time. And notice our concentrations are the same, 5 and 4. Now I'm going to speed things up. I'm going to send 2 over, and he's going to send 2 back at the same time. But wait, I've still got 4, and he's still got 5. So, we're at equilibrium. We're still exchanging back and forth, but we're not getting anywhere. We're not changing our concentration, and if these were colored, we wouldn't be changing the color of the solution either. The pressure would be the same, the temperature would be the same, even though we're still reacting. We're still sending stuff back and forth from reactants to products and products to reactants. Okay. Breakfast is over. Lunch has not begun. Sorry, Alex. Okay, Lowe's got a question though. Though some reactants remain after the concentration stop changing. The answer is yin. In our world, we're going to say, Lola, no. So we're going to say that the products can always come back and become reactants. Now, let me get rid of my candy here for a second. It's a good question, Lola. Okay, so Turns out, what was I talking about? Equilibrium, amounts of stuff going back and forth. So we got the same amount going back and forth, equal amounts changing on either side. Even if I speed up both rates like I did with Alex, so 1 and 1 or 2 and 2, and I still end up having the same amount on both sides, as long as both rates are changed equally. And I'm reading Lola's question again to see if I answered it. Reactions remain. Reactants remain. Yeah. Yes. So here, let's do an easier one. Okay. So, let's do an example. You ready? It's not a reaction, but okay, it's kind of a reaction. Check this out. I got a watch glass with water. Water. So what's happening? Some of the waters are evaporating. But let's say I got a cover on this thing. So now some of them start to go back down and condense. Oh, and once I get the same amount condensing as evaporating, then I got this going on. H2O liquid is going to H2O gas. And now if I can measure the pressure up here, the pressure would be the same, right? So if I got a constant P, then I got good evidence that I'm at equilibrium. Case in point. What if I got this and I don't have a cap on it? Well, I might have this happening for a while. Maybe one coming back, but what if I got this? Then I got H2O, and I got lots and lots of them changing to gas. So I got this, ready? H2O gas. Sorry, I meant to put a G up here. But I don't have many going back from the gas to the liquid. I only got 1 out of the 5 or whatever. So that's going to be like this. So if I've got this happening one way and this another, I'm not at equilibrium. It is not, my conditions are still changing. They are not constant. Not at equilibrium. And for one thing here, the vapor pressure would still be changing. So vapor pressure, in fact, let's say what it would be doing. Still increasing, right? If that's the case, man, I am not at equilibrium yet. Okay? Hope that helps a little bit. Some reactions pretty much all go to products. You ready? Flame. I burn my notes. No, I don't want to do that. If I burn this paper, how much ashes can I get to go backwards and become paper? Pretty much none. Okay? Without me like growing a tree and doing it real slow. So some reactions pretty much go to completion, we say. They pretty much go to the products. This chapter's not about those very much, okay? But burning stuff is generally going pretty much all to the products, okay? But this is more like what we're talking about, things going back and forth. Or like the ones from our last chapter, NO and NO2 and all that going back and forth, gases going back and forth. That's pretty typical equilibrium type idea to think about. Products forming and products reacting, going backwards to form more reactants at the same time and at the same rate. Okay, that's probably way too much more than you need. Let's see if we answered those questions. So wouldn't we, equilibrium constant, help us determine whether the reactions tend to have a higher concentration of reactants or products? Lola's ahead of the game. Lola, you're right where you need to be. And I'm going to bring everybody else with us. Okay, so Lola's saying, can we measure this equilibrium idea with a number? And the answer is yes. And it's called, she's right, the equilibrium constant. So for the rest of you, let's write what's an equilibrium constant. And ready? Here's the letter for it. Capital K, not a small k, big K, and then EQ, or we could have other letters there too, at any rate. So an equilibrium constant. Well, here's what it is in math terms. So to get the KEQ, I take the concentration of all the different products divided by the concentration of all the different reactants. However, you solids. Like solids don't have a moles per liter, right? It's just a chunk of solid or it's not. So leave out solids and liquids. Keep in moles per liter. So that would be aqueous and atmospheres, which would be gases. Okay, so you're going to keep in gases and also solutions, aqueous stuff. You're not going to have in liquids or solids because their concentrations don't change. Chunk of solid or a bit of liquid is either there or not. But if it's a solution, it can be more or less concentrated. If it's a gas, I can have a higher or lower pressure of that gas. Okay, you ready? So we just got time to play a little game. Let's say I have the same. So if concentration of products equals concentration of reactants, K would equal what number? What number, gang? If these two were equal, check your math skills this morning. If the product concentrations equals the reactant concentrations, K gonna be what? Thank you. Oh, the ones are rolling in. Thank you, Penelope, Lola, Alicia. You're right. It's gonna be 1. So here we go. 1, 1. Okay. Now I want you to make more products. What's going to happen? What's going to happen to K? So if I get the concentration of products are more than the reactants, K is going to be what sort of number? So if I got more products than reactants, K is going to be what sort of number mathematically? More products. What will happen to K? I know there's a time lag from when you type in and when I see this. What happens to K? More products than reactants. The K number will, are you still there? Yeah, now they're coming in. Thank you. Be greater than 1. Good. And of course, if it's the opposite way, if products are less than reactants, then K is less than 1. If it's something that goes to completion, like burning paper, here, let's do an example. Burning paper. Well, it's K is, of course, not just greater than 1, but K is almost infinite, isn't it? Because it just becomes pretty much all products. The paper burns mostly completely, okay? And I certainly can't go backwards. So I'll say close to infinity. Here's the infinity symbol. So infinitely big with a capital B. So some reactions pretty much are huge, okay? On the other hand, some don't happen at all. Ready? Okay, see this plastic? I'm going to write the reaction for I know we're about out of time, but this is kind of a fun one, okay? Example. Plastic dissolving in water. How much does it happen, gang? Not much. So the K is going to be really, really small. So really, really, really less than 1. You get the idea? Are you okay with K so far? We're going to look at some equations and data with it next time when I see you on tomorrow for a brief class. All right, thanks for joining me, everyone, and see you for a short class tomorrow. I sent the invite out already, so hopefully that won't be so confusing. And we don't have class, I don't think, Monday, so bye until tomorrow.